Okay, so instantaneous rate of change involves calculus, and we get what's called the slope of the tangent line. So let's define what a tangent line is, and then I'm going to set up this formula for you again graphically, and then we're going to go through and we're going to solve one of these. So a tangent line to a circle is defined as a line that touches the circle at only one point. So tangent means it touches in only one point. So here's our picture that goes with tangent line for a circle. And you can see this is, of course, just a semicircle. But do you see that line P right there? Or that's the point P, and you've got this little pink line in there. See how it just touches at that one point? It just lays right up against the curve and just sort of kisses the curve in one spot. And that is what we have is when we have a tangent line to a circle. So what happens when it's not just a circle, but it's like a curvy line? Well, tangent lines should touch the curve at one point, but not anywhere nearby. And they should indicate the direction, that should say of the curve, the direction of the curve. So it should look like the line is kind of guiding you along the curve. So one way to kind of think about it is if you had skis on and you were skiing on this mountain, the tangent line should kind of point the way your skis would point. So as we come along here, this P1, you're going up the mountain, and see how your skis would be pointed up and you're just touching one point? This is definitely a tangent line. That one's tangent. As you head down the mountain, your skis should be pointing down. This is like you wrecked and your skis are stuck in the snow or something. This one is not tangent. I know it only touches at one point, but it doesn't indicate the direction of the curve. It should be slanted down and not cutting across like that. So then you come along here, you reach the bottom of the curve, it touches in one spot, and it still indicates kind of the slope of this curve down here. That one's tangent. P4 touches in one spot, and it's indicating that you're going up the curve, so that one is tangent. And then P5, you're up at the top of the mountain and you stuck your skis in the snow. That's not right. So that one is not tangent. So it's not just about touching the curve in one spot. It has to indicate the direction of the curve as well. So that's the first thing, is you have to be able to recognize what does tangent look like on a graph. So now what I'm going to do is I'm going to develop the formula that we had on the last page, and I'm going to do it graphically. And then this definition at the bottom is the exact same thing as what was on the previous page. So we're going to start with a secant line. We're going to go from R to S. You see how we're cutting across the curve in two places? So that's a secant line. And the way you get the slope of the secant line is you do rise over run. So we're starting here at A, and then this is the y value, f of A. And we're headed over, we're going to take a step of size h, and we're going to end up over here at A plus h, and then that corresponding y value would be f of A plus h. If you want to find the slope, you do rise, which is f of A plus h minus f of A, that's your rise, over your run. Well, to do the run, that run is just h. If you take A plus h and you subtract A, you just get h. So we're just going to call it h. So that would be the slope of the secant line. And what we want to look at is what happens, how does the slope of that secant line change as your 2 points R and S get closer and closer and closer together. So instead of R being here and S being all the way up here, what if S was further down the curve, where the distance is shorter between R and S? Well, do you see how that secant line, do you see how it's flatter? And if you keep sliding down the curve, it's even flatter and flatter and flatter until eventually you hit a tangent line. R and S are so close together that it's a tangent line. It's pretty much the same point. So this would be average velocity, and these would be all average velocities leading up to an instantaneous velocity. It's like they slide down and then they hit that tangent line. And you can find applets of this, and like online, if you were to Google secant line approaching tangent line, you can see some like animations of this. So what's happening is h is approaching 0. We're trying to make this distance between the 2 points shrink until we're really just honing in on what's happening at r, and that would create our tangent line. So this is the same as what we saw on the last page, but on the last page it was called instantaneous rate of change, and now it's called slope of a tangent line, but it's the same formula. It just means it has two interpretations. You can talk about it as a rate of change, or you can talk about it as a slope of a tangent line. So this formula, again, this is a section 3.3 formula for how do you get the slope of a tangent line at a specific point A, which may not be the most efficient way to do it, but that's how we're going to start. So there's our point A. If this limit doesn't exist, then you don't have a tangent line, but most of these are going to exist, okay? All right. So here's some other notation. We're finally getting to the fact that this is called a derivative. And so other notation would be this. It's f with a little prime, like you would write it f prime of a. And that means derivative, slope of tangent line, instantaneous rate of change. Those all mean the same thing. So I just wanted to have this formula again on the page. So now what we're going to do is we're actually going to go back, that example we did with the big table about your speed as you, or the distance that you've traveled when you leave the stop sign. We're going to go back and actually do that one and figure out what the instantaneous velocity is at 10 seconds for this function. This was the function we had before. So that's distance. And right here, the role of A is going to be played by 10 because we want to find out what's happening right at 10. So this is going to be a 10. And this is going to be a 10. You're going to replace those with 10s. The first thing we need to do, this can be very overwhelming if you try to do it in one step, so we're going to do it in a couple steps. The first thing I'm going to do is just work on the numerator. So the first thing I'm going to do is f of 10 plus h minus f of 10, because I said we plug in 10s for those a's. Now when you have those little numbers in parentheses, what it means is that you're going to be plugging those into the function. So I'm going to put a 10 plus h over here for my t. So when I plug 10 plus h into this function, it looks like 3 times 10 plus h squared. And yeah, it's not really f, it's s. I guess we could change that if we wanted to, but it's the function that you're dealing with. So 3 times something squared, and the something is 10. We're going to take that, we're going to subtract this function with a 10 plugged into it. So you're substituting in a 10 plus h, you're substituting in a 10, and you're subtracting. And now it's a matter of working all of this out. We're going to need to do FOIL right here. What do I mean by FOIL? I mean that we need to take 10 plus h times 10 plus h. That's what it means to square something. And we want to do first, outside, inside, last to multiply that out. So what we're going to have, first you get 100. On the outside you get 10h. And on the inside you also get 10h. So that's going to make 20h. And then on the far end here, you're going to have an h squared. So this is 10 plus h squared, all multiplied out. Okay. Minus, this you might be able to do in your head. Do the exponent first. That would be 100 times 3, 300. Okay, now what we need to do is we need to distribute. I'm going to distribute my 3 through everything here in parentheses, and I'm going to get 300 plus 60h plus 3h squared minus 300. And then you want to look across there because almost always something's going to cancel. And you'll notice that you have a 300 and then you have a minus 300, so they go away completely. They actually add to 0 and they're gone completely. So all you're left with is that guy. So now what we can do, now that we've kind of simplified the top, I'm going to put it all together. I'm going to say the derivative at 10, or the instantaneous velocity at 10. Again, I probably should use the letter s because it's s, but I'll leave it as a function, is the limit as h goes to 0 of this thing that we're left with, 60h plus 3h squared, all divided by h. And then that just became a problem like what I taught you how to do before. If we plug a 0 in for h, the problem is we're going to end up with 0 over 0, which means you're supposed to like factor and cancel and that sort of thing. Well, you can factor an h out of the top and then cancel it. Or if you want to bypass that factoring step, you can just notice that every single term has an h. All three have an h. So what you're allowed to do is just cancel one h from everything. So I'm going to say cancel h. So cancel this h, and cancel one of those. It's going to leave you with one. And what you're going to be left with is you no longer have a denominator because we canceled it. So it's like a 1. So we're left with 60 plus 3h. And now we've gotten rid of that 0 over 0. We can now try to plug in. If you plug a 0 in there for h, this whole last piece goes away, and you are left with 60. Surprise, surprise, a couple pages ago when we did that table, what did we say? We said it was 60 feet per second. But this is the process you would do to show it. Now, this is what I mean by it's not terribly efficient, because what if I wanted to know what was happening at 15 seconds? Well, you need to make those 15s, and then you have to redo everything. Yeah, nobody wants to do that. What if you wanted to know what was the instantaneous velocity at 5 seconds? Put in 5s, redo everything. You're redoing all of that algebra, all of that FOIL, the canceling every time. It's extremely inefficient. So a better way to do this is to do it the way that they explain in section 3.4. So this will be in section 3.4, and this is, I think, the preferred way to do things, and that is we're going to do this generically, and we're going to do this whole mess up here. We're going to do it once generically, and then all we have to do is plug in a 10 or plug in a 15, plug in a 5. It's super easy at the end. So we're going to do it generically with x's, and I think you're going to like that a little bit better. Now, just as a heads up, when you're doing the homework in section 3.3, if you go to view an example, they're going to work you through the long way. So you may want to use the notes instead of view an example. All right, so here's now our formal definition of a derivative. This is the one you want to memorize. You got to know that one. And it's called the derivative of f with respect to x. When something has a derivative, we say it's differentiable. And this process is called differentiation. These are some of the biggest words I know, right? They all start with D. So here's the difference. If we look at this little chart here, this side of the chart is algebra. You only need algebra. Over here is calculus. That's just slope. Slope of a secant line, average rate of change, average velocity. And if you want to tie this into business, average rate of change for cost, average rate of change for revenue, average rate of change for profit. If you want to talk calculus, where we now put a limit, now we're talking about instantaneous rate of change, instantaneous velocity. It will be a slope of a tangent line. And this is the big kicker we're going to get into in this class, is marginal cost, marginal revenue, and marginal profit. If you've taken economics, microeconomics in particular, you've probably heard of this. But in your economics class, they didn't teach you calculus, so they taught you sort of like a way to do it with tables. You're going to really learn what's all the calculus behind marginals in this class. So that's kind of where we're headed. So I like this table a lot. It's a nice comparison between what you can do in algebra and then where calculus can take you once you know how to do calculus.